Welcome back, everyone. We've got a real head-scratcher on our hands today.
Oh, yeah. What's that?
It's a paper that dives into the really small stuff, quantum mechanics territory.
Always fun.
It's called Physics of Virtual Interaction by Dmitry Plotnikov. And let me tell you, he doesn't hold back.
Sounds intriguing. What's the main thrust of his argument?
Well, he basically says some of the things we think we know about particles at the subatomic level, like how they behave, they might not be the whole story.
Really? Like what? What kind of things?
So he's not saying quantum mechanics is flat out wrong, right?
Yeah.
But he thinks there's a missing piece of the puzzle, this thing he calls virtual particles.
Virtual particles. Okay, we're going to need to unpack that one.
For sure, for sure. But first, let's make sure we're all on the same page. You know, those basic principles of quantum mechanics we all learned in school, things like
Discrete energy levels?
yeah, the Pauli exclusion principle, Heisenberg's uncertainty principle, all that jazz.
Cornerstones.
Right. Well, Plotnikov argues that sometimes the way we apply those principles, it doesn't quite match what we actually see in nature.
Oh, interesting. Give me an example.
Okay, think about the simplest atom, hydrogen. One proton, one electron, right?
Yeah.
Super basic.
Right.
But here's the thing. We never find single atom hydrogen out in the wild. It always hangs out with a buddy, you know? Molecular hydrogen, H2. Two atoms paired up.
Yeah. I guess you're right.
So if those protons and electrons are supposed to be acting like all nice and coherent, what's the deal with the pairing? What's holding them together?
Good point. So does he have an explanation for that?
Well, he uses this simple example to point to a bigger issue, the nuclear force. The stuff that binds protons and neutrons together inside the nucleus.
Right, the glue that makes atoms possible.
Exactly. Current models say it works through this exchange of particles called mesons, bouncing between protons and neutrons.
Okay.
But according to the coherence principle, protons and neutrons shouldn't even be able to interact that way. They're not coherent particles.
So how does he reconcile that? Because, I mean, obviously nuclei exist, so...
Right. And this is where those mysterious virtual particles come in. Could they be the secret ingredient in our nuclear glue? What do you think?
I'm hooked. Tell me more.
All right, to get there, we need to talk about the most famous experiment in quantum mechanics, the double slit experiment.
Ah, yes, the double slit, where you fire electrons at a barrier with two slits, and they make that wave-like interference pattern on the screen behind it?
Yep, as if each electron went through both slits at the same time. Mind-bending stuff.
Right. Classic demonstration of wave-particle duality.
But Plotnikov points out a bit of a snag. Not all electrons are created equal. Different energies, different spins.
Yeah.
So if they're not all identical, how do they all make that same interference pattern?
So what's his alternative then? Does he say electrons actually split in two?
Well, he proposes something even weirder. He thinks an electron could be in two states at once, spin up and spin down, and each of those states can go through a different slit.
Whoa, hold on. So it's like the electron is making a quantum copy of itself.
That's one way to visualize it. He calls these separated quantum states virtual electrons.
Virtual electrons? Okay, I'm with you so far.
But here's the kicker. These virtual electrons don't exist independently. They're like ghostly twins of the real electron.
Okay, ghostly twins, got it. So we've got our electron, it makes a couple of ghost clones, each with different spins, and they go through the different slits. Then what? How do they create the interference pattern?
Good question. The typical explanation is that they exchange photons, those little particles of light.
Right. But Plotnikov takes issue with that, right?
He does, because remember the Pauli exclusion principle? It says that two identical particles can't occupy the same quantum state at the same time.
So no two electrons can have the same spin if they're in the same energy level. Got it.
Exactly. So if these virtual electrons are swapping photons to make that interference pattern, for a split second, they both have the same spin.
Which breaks the rules.
Big time. So it seems like Plotnikov's solution creates another problem. How does he get out of this quantum conundrum?
Well, he introduces another mind-bending concept, the virtual photon.
Virtual electrons, virtual photons. How much more virtual can we get? My head's already spinning.
I know, right? But bear with me. This is where it gets really cool. So imagine a regular photon, right? It's like a speeding bullet. Zip, 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 at the speed of light.
Right.
But a virtual photon, it's more like those little stepping stones you use to cross a stream.
Okay, so instead of zooming across space, it's popping in and out of existence at specific points.
Precisely. Like a quantum game of hopscotch.
I like that image. But hold on. If these virtual photons aren't bound by the speed of light, doesn't that kind of mess with Einstein's whole theory of relativity.
You're sharp.
Yeah.
And that's a point that Plotnikov tackles head on. He basically says that virtual particles, like those stepping stone photons, play by a different set of rules. They're not stuck in the same space-time constraints as regular particles.
So they're like little quantum rebels breaking all the laws of physics.
Well, you could say that. But here's the thing. This idea of virtual particles operating outside of space-time, it might not be as crazy as it sounds.
Oh, really?
Yeah, in fact, it could be a key to understanding some of the biggest mysteries in physics, like gravity.
Whoa, gravity. How do virtual particles tie into something as massive as gravity?
Plotnikov proposes that gravity itself might be a result of, you guessed it, virtual particle interactions, specifically the exchange of these little guys called gravitons.
Wait, so instead of picturing gravity as like a bowling ball on a trampoline, warping space-time, we're talking about this constant exchange of virtual gravitons.
That's the gist of it. And this idea could potentially solve some of the puzzles about gravity that still have physicists stumped. Like, why is gravity so much weaker than the other fundamental forces? Maybe because those virtual gravitons are playing on a whole other level outside the normal rules of space and time.
Okay, I'm starting to see how Plotnikov's ideas, though definitely mind-bending, might crack open some major cosmic mysteries.
And that's just the tip of the iceberg. He even suggests this framework could shed light on the early universe. Imagine the Big Bang, not just as this big chaotic explosion, but a universe teeming with these virtual particles.
So these tiny particles were like the architects of the early universe, setting the stage for everything that followed.
That's a great way to put it. These virtual particle interactions might explain how the universe expanded so fast and so uniformly in those first few moments.
Fascinating. So we're saying these tiny, almost invisible things could hold the key to some of the biggest questions about the universe.
Exactly. Things like the nature of dark matter and dark energy.
Ah, yes. Those invisible forces shaping the universe. I've heard those are a real head-scratcher for physicists.
They are. But what if those elusive entities aren't made of some exotic new particle, but are actually the result of all these virtual particles working together, interacting in ways we're just starting to grasp?
Okay, so the answers to some of the biggest mysteries in cosmology might actually be found in the tiniest building blocks of the universe. That's pretty mind-blowing.
It is, and that's what's so amazing about Plotnikov's work. It connects that micro world of quantum mechanics to the macro world of cosmology in a way that just makes you rethink everything.
It definitely does. But let's bring it back down to Earth for a second. All this talk of virtual particles and the early universe is incredible, but does it have any practical applications for us here and now?
Oh, absolutely. Just think about one of the most exciting areas in technology today. Quantum computing.
You mean those super powerful computers that use the quirks of quantum mechanics to solve problems that regular computers can't even touch?
Exactly. And Plotnikov's work could be a game changer for this whole field. Remember those virtual photons that can transmit information instantly? What if we could somehow harness that power to build quantum computers that are way faster and more powerful than anything we can even imagine right now?
Wow, that sounds like something straight out of science fiction.
It does, doesn't it?
Right.
Think about it. A world where we can use these super advanced quantum computers to design life-saving drugs, create incredible new materials, even simulate the human brain.
The possibilities are pretty much endless. But let's not get too carried away. Quantum computing is still in its early stages, right? We've got a lot to learn before we can really tap into the power of these virtual particles.
True, but Plotnikov's model provides a roadmap for where quantum computing could go. It reminds us that even the most theoretical ideas can end up having a huge impact on our lives.
So, pushing the boundaries of knowledge, being open to new ways of thinking about the world, it all matters.
Absolutely. But there's another fascinating layer to all of this, one that takes us beyond technology and into the realm of philosophy. Think about Plotnikov's model and what it implies about the nature of reality itself. If these virtual particles can really interact instantly across vast distances, what does that mean for our understanding of cause and effect?
Yeah, if those virtual photons are like a cosmic Morse code, transmitting information outside the limits of time and space, does that mean the universe is even more interconnected than we ever imagined?
It's a mind-blowing question, isn't it? It's like, instead of thinking of time as a straight line, we need to imagine it as this vast, interconnected web where everything is happening all at once. It really makes you question everything we think we know about how the universe works. Plotnikov's model is suggesting that cause and effect, Those basic building blocks of how we understand the world might not be as simple as we thought. If these virtual particles can just ignore the normal rules of time and space, then the lines between past, present, and future get all blurry.
So instead of thinking about time as this linear thing, with events happening one after another, like a neat little story,
Right.
maybe it's more like this big, messy, interconnected web, where everything's happening all at once.
It's a wild idea, isn't it? Makes you think about time as this giant ocean where everything is kind of swirling around and connected.
Yeah, it's a lot to wrap your head around. But speaking of things that make your brain hurt, let's go back to that big question Plotnikov's paper brings up. Is our current understanding of quantum mechanics the whole picture? Or is there something more?
That's the question that has physicists debating, right? Plotnikov's model, with all these virtual particles and their weird behavior, definitely pushes us to think about what we might be missing. Maybe we're just seeing the tip of the iceberg when it comes to what's happening at the quantum level.
It's like we stumbled across this amazing new language, quantum mechanics, but we're still fumbling around trying to understand the grammar. We can put together a few simple sentences, but we haven't figured out how to write a sonnet yet.
That's a great way to put it. And Plotnikov, with his focus on these virtual particles, is basically suggesting a whole new set of grammatical rules, a new way to appreciate the poetry of the quantum world.
But like any new theory, the real test is whether it holds water. Can Plotnikov's model make predictions that we can actually test out in the real world?
Right, in science, it's not enough to have a cool idea. It's got to be more than just a pretty theory. It has to make testable predictions, things we can confirm through experiments.
So how would we go about putting Plotnikov's model to the test? Where should we be looking for evidence of these virtual particles and their weird effects?
One area that's super interesting is quantum entanglement. You know, that spooky action at a distance where two particles are linked, even if they're miles apart.
Oh yeah, that's the one that even Einstein had trouble with. It's like they're sharing secret messages instantaneously, no matter how far apart they are.
Exactly. And Plotnikov's model with those virtual particles flitting around outside of space and time could give us a new way to understand how that seemingly impossible connection works. If we can design experiments that let us measure the timing of these entangled particle interactions really, really precisely, we might be able to see evidence that supports, or maybe even refutes, Plotnikov's ideas.
So basically, we need to see if those entangled particles are truly talking to each other instantly, or if there's even the tiniest delay that could give away the game. Show us how these virtual particles are working behind the scenes.
Exactly. And another exciting avenue for testing Plotnikov's model is in the search for dark matter and dark energy. Those mysterious things that make up most of the universe but are completely invisible to us.
Right, like cosmic ghosts. We know they're out there, but we can't see them or touch them.
Exactly. What if, like Plotnikov proposes, these invisible forces aren't made of some exotic new particle that we haven't discovered yet, but are actually the result of tons and tons of virtual particles all interacting in this vast network of instant connections?
So the answer to some of the biggest mysteries in cosmology might be hidden in plain sight, right there in the smallest building blocks of reality.
It's a mind-blowing possibility, isn't it? And experiments designed to detect subtle fluctuations in space-time or to look for other clues about these virtual particle interactions could give us a whole new understanding of dark matter and dark energy.
It's incredible to think that the key to understanding the vast universe might lie in these tiny, elusive particles that we can't even see. But regardless of whether Plotnikov's model turns out to be right in the end, the questions it raises and the new ways of thinking it offers are invaluable.
Absolutely. It's that kind of bold, out-of-the-box thinking that drives scientific discovery. Sometimes the most groundbreaking discoveries come from challenging what we think we know and being open to completely new ways of seeing the world.
And on that note, I think we've given everyone a lot to think about today. We've explored this fascinating world of virtual particles, from their potential role in the behavior of tiny electrons to the grand scale of the universe, and even how these ideas might shape the future of technology.
It's definitely been a journey. We've tackled some pretty mind-bending concepts today. And though there are still so many unknowns, it's exciting to think about all the possibilities.
It just shows that science is this never-ending adventure, a quest to learn more about the universe and our place in it. It's a journey full of twists and turns, and it's always leading to more questions.
Exactly. So, as you all continue to ponder the mysteries of virtual particles and the nature of reality itself, we encourage you to stay curious. Keep asking questions and exploring.
You never know what amazing discoveries are waiting just around the corner. Until next time. Keep diving deep.